Okay, so for today's lecture, I want to pick up exactly where we last left off. So as you might recall, we were talking about the IEEE floating point representation and the power of expressiveness it allows for us to try to capture very large numerical encodings, binary encodings for very large numbers, or very small numbers by using a portion of the bit sequence to represent an exponential value, because that allows us then to take a base value to multiply to some exponential value on a power of 2 basis to represent numbers that can grow very large, or either on the right side of our binary point, on the right or on the left side of our binary point. Okay, so to really highlight why this is both good but comes with its own pitfalls, we're going to look at some examples, some toy examples of tiny floating point numbers. Now, the floating point numbers that you use inside your system are typically either going to be a single precision or double precision. That single precision is a 32-bit encoding. That double precision is a 64-bit encoding. Over the course of this class, I want to see what happens if we try to use the same schema, but on like an 8-bit encoding, on a 6-bit encoding, on a 5-bit encoding, even on a 4-bit encoding, to see what numerical values we have and to really get an idea of what it means for floating point numbers to be approximations. Will really motivate that when you start seeing it in tiny scope. And actually, I have developed a little bit of a small C code, which is now already available on our GitHub repo, so that you can examine the code and actually get the same output for yourself. So before I do that, I just want to ensure that everyone is comfortable and familiar with the floating point values. Typically, we treat them in one of 3 cases. We have denormalized values, which are those cases that are typically smaller than 1 and trend towards 0. So the closer you are towards 0, the more of the denormalized zone you're in. And then those that fall outside and go toward further away from our 0 scope are our normal values, our normalized values, and the ones that fall into the range of infinity or undefined or not a number are going to be our special cases. And so we're going to, again, look at each of our encodings in our tiny cases to see when we have to define an infinity, when we have to define a 0. A 0 in itself is a special case, although that's when our entire binary sequence is all zeros. Or if our bit sequence is 1, it's possible to have a negative 0 inside a floating point representation. As I said before, we'll see that today. And then we'll take a look at when we get our normalized and denormalized values. So up to this point, does this chart at least seem understandable and parsable in terms of what we're talking about, in terms of defining just what a denormalized versus a normalized value is, and then our special cases? Excellent. I'm seeing a lot of head shaking. Okay, so then let's go back to our representation. So we said that when we have a binary sequence of n number of bits, we partition it into 3 segments to represent a IEEE floating point number. 1 bit, regardless of how many total bits are allocated towards our encoding scheme, is always going to be used for our sign bit, so that we can have both positive and negative numbers. And that's always going to be our most significant bit. Now, in our tiny floating point example, we're going to actually create a 1-byte float. So in order to do this, in order to maximize what we can do here, we're going to go ahead and prioritize the 4-bit encoding scheme onto this exponential value, and then the 3-bit sequence on my fractional value. So remember, this is kind of the base that gets multiplied by the 2 to the power of whatever value, which will be represented by my 3-bit value here. So let's take a look if we take and actually try to run a representation of that inside of C. So the first thing I'm going to do is, well, I don't think I had set this up. We're going to have ugly code today because I'm on my secondary machine. I haven't configured my my syntax highlighting on my Vim inside this machine. So I'll have to set a profile up for this, but this is great. You'll get to see what code inside of Vim looks like if I use the default settings. And this is a good day for it because I'm not so concerned about the implementation details. I'm more concerned for you to see the actual set of values that are possible using an 8-bit encoding. Okay, so let us take a look at this. Yes, very ugly code because now it's all just white text on a black background. Okay, and here, let me start to go ahead and run this. And then I'll just show you some of the highlights of the code that's worth mentioning. But what I really want to see is, and then we'll call this 8-bit. What I really want to see here is going to be the results of this. So while that's compiling, one thing you can see here that I'm using is I'm going to create a struct that is going to represent the 3 partition sizes for my tiny float. So in this particular example that we're going to look at, my sign bit is 1, right? Because we're going to have 8 bits that represents our tiny floating point numbers. 4 bits are going to be reserved to our exponential value, our EXP, and 3 bits are going to be reserved for our frac. So that's going to be our Okay, so with that said, I'm going to create a helper function that's going to go ahead and print the state of my tiny float in terms of its binary vector, which is each of its partitions, what is the value of each of its partitions. And then I'm also going to define whether that sequence represents a special case, whether that sequence represents a denormalized case, or whether that sequence represents a normalized case. And then I'm actually going to show you what the values, the translated value based off of the IEEE standard would be to parse that based off of a 8-bit sequence that's subdivided the way we see here. Okay, let's actually run this. And then here, I want to say inside my main, you can see I'm just going through and I'm going to iterate and loop over every possible value that I can encode in a tiny floating point number. So this will show you effectively the exhaustive, complete set of values we have if we limit ourselves to 1-byte floating point numbers. And then I want to look at smaller ones too, so we can actually get something a little bit more surveyable. But even this, you'll see how tiny this ends up being and what the values are. So here we can see, so an example here, we get a decent number of values, right? Like we know how much encoding we can do using a full byte. That's going to be 256 different representations. So here we can see that I have my 0 value. I have my denormalized values, which are going to be close to 0. And you can see how small of 0, even with just a single byte, we can get. Now, keep in mind, this is the exhaustive list. So we don't have any values inside of our tiny float data type that's in between these. So when we do any kind of math, just like you would in an integral math, you're actually hopping from one unit that's available to you to the next unit. That's what we mean by approximations. We're going to really see the consequence of this when we start talking about adding floating point numbers together and multiplying floating point numbers together. So what you see here is every possible representation. So you can see we have these very small values. And then once we get a little outside of that bandwidth of what we consider close to 0, you can see we start hitting our normalized values. And this is all based off of what's inside of our EXP register. Remember, in our EXP register, partition, not register. This isn't machine code. But inside of our partition here, if it's all zeros, that's the case where we say it's a denormalized value. And that is always going to resolve to something that's very small. The moment we start encoding a 1-bit anywhere inside of our EXP space, then that's when we start our normalized values. That's the more definite conceptual term where when you look at your bit sequence, you know just by examining the zeros and the ones, whether it's a normalized or denormalized value. Here you can see we're incrementing up with our normalized values, and we go all the way up to 240. And we can go all the way to minus 240 with an 8-byte sequence. But notice, and this is where I was trying to stress last time, but I think when we can see the exhaustive set of values that's given to us, you could see what it really means to be an approximation inside of a floating point encoding. If you see here, I jump from minus 224 to minus 240. I don't have a representation between that. So if I'm doing addition and I'm limited to a single byte floating point representation and I'm adding two values together, I have to do a lot of rounding to decide which is the next unit I jump to if I don't have it available to me as one of my representations. This is why it's super dangerous to use floating point numbers for anything that really requires precision. I know they talk about that in 1583. They probably talk about that in 2120. They probably mentioned it in assembly. And even in assembly, you probably were starting to cover these concepts. It sounds like you're starting to talk about this inside of computer org, right? So I don't know, maybe in computer org, they'll show the same thing where I think this is valuable though, to see exactly what it means to be an approximation, be a consequence of trying to get those very large representation with a finite number of bit sequences means that you have holes in your number sequence between values. And so that can cause erroneous behavior, which is why it's always, always, always better to use doubles over floats. Gives you double the precision. And when you're always dealing with an approximation, especially once you start operating on it, once you start adding to it, once you start subtracting from it, once you start multiplying or dividing with it, you are going to get something that's close, but not maybe exactly to what was there, which is why we start using the rules similar to in calculus, where whenever you do have to compare anything that is a floating point approximation, you use some error thresholding to say if it's at least within this distance of this other floating point representation, then it's effectively the same. Now, fortunately, 64-bit encodings give us a very deep pool to go ahead and utilize. This is, and actually, let's keep getting smaller. That was the entire point. So here, we're looking at the 8-bit. Let me move this up here. Is it that way? Okay, so now let's do, because I want to keep going down this rabbit hole. We see the range of an 8-bit. Looking at 6-bit, suppose then I want my sign bit to be 1 bit of encoding space. I want my exponential to be 3 bits, and I want my fractional to be 2 bits. So let's clear this. Let's now and what is this? Let's call this 6-bit. Okay, so this is, as you can see, based off the source code, the same encoding scheme, we're just reducing. And we're going to see what consequence that has by just removing 2 bits from our encoding scheme. Now you can see the exhaustive list we have is much smaller than what we had before. You can see that our denormalized numbers are further away from 0 than we had before. We don't have as many spaces, as many binary sequences on just 2 bits to get a lot of denormalized values. Because remember, that fractional space represents how many denormalized values I can have. The exponential space represents the number of normalized values I can have. And then this would be my normalized values here. And then in this representation, I have a min to max of from 14 to minus 14. And then you could see when I have all ones inside my exponential field, that's when I'm going to have like my infinity and my nans. You'd see if it's anything in between all zeros and all ones, that's my normalized space. When my EXP field is all zeros, that's my denormalized space. And when it's all zeros for the bit sequence, it's a 0 value. Actually, I think I can tie this in to so I think the book gives for the 8-bit sequence like a chart that you can look at. I think it's much easier just to see the source, the output from our console log. But going to the 6-bit format, which is also an example given in the book, what the book gives is this. So what I wanted to do was map the exhaustive list so we can actually inspect it towards this set of values that are plotted across an axis, a numerical axis. So notice we get the way that the IEEE floating point standard works now that this is surveyable, because usually when you're talking about 32-bit encoding, 64-bit encoding, you can't really survey the number of values you can encode. When it's 6 bits, you can. And in fact, we'll go smaller and smaller all the way down to 4 bits. We're not going to go any lower than 4 bits on this. But you can say that an affordance that's given to us in this encoding scheme is it propagates a lot of our encoding priorities towards the 0 space and immediately around there. Look at how dense and clustered our set of normalized values are. Our denormalized values, as we already saw, when we only have 3 bits to encode, is going to be 8 denormalized values. That makes sense, right? That's the number of combinations you can have for 3 bits when your 3 exponential bits or exponent bits are zeros. So we'll have 8 values there. And then the rest of the values are going to be normalized. But notice as we get to the extremes, our holes get larger and larger in between values. And then finally, the very ends represent our infinity. So this is, all this is doing is mapping visually this right here. Does that make sense? Is this giving you a more realistic understanding of what the floating point representation is actually doing in binary? Like, at the end of the day, all we're really talking about is how we're saving our data, how we're storing our data, our representations, whether in this instance it's fractional numbers, before then it was integral values in binary sequences. But it's important to understand the limitations of our encoding schemes. And I think you can kind of see now, based off of the formula we presented, the 3 independent variables that or states that a floating point representation requires, that given a particular sequence, what our max number of representations are. Make sure there's no comments here. Perfect. Okay, let me see here. Is there going down this list? Okay, so if we were to zoom in on that visualization now, because again, you could see we have a dense clustering of our normalized terms, and then we just the 8 denormalized terms. You could see right here, those will be those 8 denormalized. Some will be on the negative side, some will be on the positive side, and then 0 counts as one of those encodings. And then notice how the spacing is kind of evenly distributed all the way from minus 0.5 to 0.5, and then it starts to elongate, and it'll continue to elongate as you keep stepping further and further from your zero encoding. Okay, so here is an example of a 5-bit case, again, pulled from the book. Now we can either view this on the chart just like this, where it shows our bit sequences, where the first, it's subdivided into 3 partitions. This first partition is our sign bit. The second partition is our exponent bit. And this third partition is our fraction bit. So we can see, translating this into the given formula, we can re-evaluate it as the value or its decimal representation. So 0, 1/4, 1/2, 3/4, 1, 5/4, 6/4. In fact, if we want to see the exhaustive list, I just so happened just to go ahead and make a C code to show you that this chart lines up exactly if we were to implement this in C and display all those values in C. So let's take a look at that. Let me cancel out of this. Let's do this, 0, 3. No, I want, I guess 0, 4. For some reason, I jumped to 4-bit instead of 5-bit. Okay, so here you can see, just like in that representation here, and let me clear this before I start talking. 0, 4. Yeah, that's perfect. Let's call this 5-bit. So just like you saw on that example table, the first bit in the partition bit sequence would be the sign bit. The next 2 bits would be your exponent bits, and then the next 2 bits are going to be your fraction bits. Okay, let's see what, and then we will compare to the table. So you can see, if we look at our normalized, our denormalized, what our infinity values and NaN values are all mapped to. Like I was saying earlier, we actually have 2 mappings for 0. This is when the sign bit is 1, so that's actually a -0. This is when our sign bit is 0, so that's a +0, right? Just a consequence of this mapping scheme. And then we approach unilaterally both ways. And of course, obviously, the reason why we need to have a -0 is so that we have an even distribution of spaces between our zeros, right? So we want to be approaching from both ways. So it's evenly divisible for our representation purposes. That's super important with our floating point numbers, since we want to support signed and well, negative and positive numbers in the same way, and not have an offset amongst them. Okay, so actually, if you look at these values, right, 0.25, 0.5, 0.75, 1, 1.25, 1.5, 1.75, 2, 2.5, 3, 3.5, that's the max number we can get to with 5 bits, right? And so here you see that that maps quite cleanly to what the book gives you. So just some source code that I think helps supplement what the book gives, so you don't have to just trust it, you can actually see it. And you can actually see the code that represents these very tiny floating point representations. And so here we can see both the fractional depiction and then the decimal depiction for only when the sign bit is 0. And then the NaN and the infinity encodings. What you're going to see that's also included here is when the sign bit is 1. And so then we're just taking those same set of values and we're applying a negative sign in front. But the actual magnitude of the value is the same. Okay, and just for fun, let's look at the 4-bit representation. Then we'll just move on. Then we would have looked at tons of tiny bits, or tons of tiny floats. So here, to try to represent a 4-bit representation. For our sign bit, we'll just have 1 bit. For our exponent bit, we'll have 2, and then for a fractional bit, we'll do 1. And I think this one, no, is 3. Okay. And the reason why I want to do this is because this is incredibly surveyable. Okay, so with 4 bits, we don't get a lot of encoding space. So we could see our exhaustive list is just these sets of values. So notice I have my 0 term, my denormalized term of 0.5 and minus 0.5. So I only have 3 denormalized terms with this 4-bit representation. The rest are my normalized terms, which would be 1, 1.5, 2, 3, and minus 1, minus 1.5, minus 2, and minus 3. And then anything outside of that is an infinity value. Then we just go to infinity or not a number. So if I were to try to use this to do math, those are going to be the only values that I can map to whenever I do my operations, like an addition operation or a multiplication operation. That would be the exhaustive list. Now, we don't encode any numbers in like 4 bits, but the entire point of this is just to show you that we are afforded a max number of values. And so this has huge consequences for addition and multiplication, division and subtraction, all your other arithmetic operations. And that's what we're going to look at next. So we have to know, what are we going to do if we try to add 2 floating point numbers and that value is just in one of those holes that makes up our sequence? Well, then we have to use rounding. By default, that is the solution. Let's look at the different rounding schemes we have as well. So in rounding, you could either round to even, you can round towards 0, you could round down, or you can round up. There's lots of ways. So so every time we produce some kind of arithmetic operation, we would do the operation like normal, and then we would round down to the next like value that's actually encoded for us. So here, the entire point of rounding is to try to find the closest representative value given the values that we do have. So let's kind of explain the behavioral differences between these rounding. The one that's used by the IEEE is this round to even. The idea behind it is it rounds to the closest value. So for instance, if it's 1.4, it would round down to 1. If I'm rounding to in this instance, if I'm rounding based off of the nearest integral unit to keep it simple, but in IEEE, it would round to the next unit it can map to. So suppose I'm mapping to the integral units, then 1.4, the next closest one would be 1, right? 1.6, the next closest one would be 2. Now, you always have in this concept of rounding this odd choice where what happens if you're evenly distanced between 2 values. So in the instance of an integral and in the instance of base 10 math, what happens if it's 1.5? Do you go to 1 or do you go to 2? And so for round to even, you round to the nearest even. Does that make sense? So if it's 1.5, the nearest even would be 2. If it's 2.5, the nearest even would be 2. Does that make sense? So round to even is really communicating that on the edge case, that it's a 0.5 value, that you have equal distance. Well, the equal distance you're going to be between is an odd number and an even number, so you always choose the even number. And that is the basis that it uses for its rounding logic. Okay, let's talk about round towards 0. Round towards 0 means that you round positive numbers down, and negative numbers up, right? So minus 1.4 would get rounded. So round to 0, you're rounding towards the direction of 0, right? In both directions. Round down means that both positive and negative numbers are go downward, and round up means both positive and negative numbers round upward. Okay, these are text descriptions. I have another slide that actually gives examples. Let's actually look at the examples and just make sure everyone kind of understands the behaviors, because as we stated, rounding is a critical part. It's a fundamental part. It's an inherent part of floating point representation for doing operations on, which is crazy, right? We already said that just taking a floating point representation was already lossy. And now what I'm saying on top of that is operating on two floating point representations is even more lossy. Okay, so round to even, let's look at this. 1.4, well, that's going to go to 1, right? Because that's not an edge case. 1.6, that's going to go to 2. 1.5 is our edge case, so we round to the nearest even number. That's going to be 2. 2.5, we're going to round to the nearest even number, so that's going to be 2. Minus 1.5, we're going to round to the nearest even number, which is going to be minus 2. Let's talk about round towards 0. Here at 1.5, we're going to round towards where 0. We're trying to go in the direction of 0, so we'll round that down to 1. 1.6, we're going to round that down to 1. 1.5, we're going to round that down to 1. 2.5, we're going to round that to 2. And then minus 1.5, we're going to round that to minus 1 because we're going in the opposite direction. So when we're talking about rounding down, that means we use the similar behavior regardless of if it is a positive or negative value. So on the instance of 1.4, we round that down to 1. 1.6, we round that down to 1. 1.5, we round that down to 1. 2.5 is 2. Finally, minus 1.5 gets rounded down to minus 2, right? So we're always shifting towards the left, which in this instance made the number more negative, right? A bigger magnitude versus a smaller magnitude versus the positive version. And then on rounding up, it's going to be the opposite effect between positive and negative numbers. So my 1.4 becomes a 2, my 1.6 becomes a 2, my 1.5 becomes a 2, my 2.5 becomes a 3, my minus 1.5 becomes a minus 1, because we're shifting towards the next right-hand side value. So again, look at the difference between my 1.5 and my minus 1.5. This comes to a 2 versus a minus 1. So that obviously we don't want to round down and round up because we get different behaviors depending on whether it's a positive or negative value. One reason why we avoid those rounding schemes, why the IEEE avoids those rounding schemes. And then round to 0 gives a more kind of consistent behavior. But the reason why you don't necessarily want to always round down to 0 is because you're always kind of truncating the number in a way. And so sometimes if you're trying to round in a way that you're not always losing value, but sometimes gaining value, that's what's afforded to you by round to even. Sometimes you're bumping it up, sometimes you're bringing it down. So statistically, it provides a more reliable behavior in terms of mapping to something that we would expect. So that's why you're probably using a rounding scheme you've never seen before. I'm sure you've seen all the other ones, right? Yeah, so why round to even? As we stated earlier, it avoids those statistical biases in calculations. So half the time we're rounding up, the other time we're rounding down. And now in terms of examples, the examples where we'd actually see this is not usually on integers, right? It's going to be when we start talking about these numbers where we're going down to the lower precision points, where we're having to examine the granularity and take the next set of points that are going to be on the far end of our radix point. So these are just some examples to show that how both these values, this 1.235 and this 1.245, would round down to 1.24 if we looking for 2 precision points versus, what is that, 3 precision points. And of course, that's why rounding matters, right? Because you're always looking at how do you fit whatever you have based off of the precision points that are afforded to you. Okay, I think everyone pretty much kind of gets an understanding. Is everyone pretty comfortable with this concept? Okay, so again, the real motivating behind this rounding is because it has major consequences on all of our arithmetic operations. For when we decide to add, when we decide to multiply or subtract, or we divide. So the basic idea here is we would first compute our exact result. And then now we can have that exact result mathematically, but based off of your bit sequence, you might not have a representation of it inside of the system. If you're using a float, it's possible, even if you're using a double, it's possible that the resulting value is non-existent in the encoding. So you first would compute that, then make it fit into your desired precision, then possibly overflow the exponent if it's too large, and then you round to fit into your fraction partition. That's the general concept of how we manage the operations so that it goes from a mathematical, theoretical component into a practical, applicable systems implementation. Okay, and again, if we're going to do any kind of floating point values, just like we said with integer addition, you needed to make sure your binary sequences were the same size, and so you would sometimes pad zeros so that you always use the same number of bits in each operation. The concept's the same with our fractional values as well, our floating point values. We have to ensure that all of our binary points line up, and if necessary, you zero fill the least significant bits before you do the addition. That seems pretty obvious though, right? But it's going to be stated just so that everyone's on the same space with that, so that everyone's on the same concept with that. And then here, and then we have multiplication. Okay, so let's take a quick example of what floating point addition looks like. Now, you already know what it looks like clearly because you've coded using doubles and floats as early as Java 1. So let's look at what floating point addition looks like and why it can be, and what it means for that rounding concept to actually occur by doing it, by defining it on our 5-bit tiny float. So here, let's take a look at this. No, not multiplication. We want, okay. So we have some source code here. Again, I'm not super interested in the source code because I'm not really entailing you to implement your own fractional numbers. I'm just showing you that this is available and that you can see at least what the makeup is of our floating point value. We'll have 1 bit for the significant, the sign bit, 2 bits for the exponent bit, and 2 bits for the fraction bit. We've already seen this implementation before, just a moment ago. But now what we've done was we've added a ability, add tiny float, that takes into float values, and we'll add them together and apply the rules that are stated for the IEEE. And we're going to see what the result of that is. So I'm more concerned about what the resulting behavior is going to be, because I think that's what's more critical for you to understand. So was this 5? Yes. Okay. And let's call this add. So here, let's run my, oops. So let's run add. So the first thing I'm going to do in add is just to remind you what is the complete set of numerical encodings that I have for my 5-bit floating scheme. So I show that all the values, and then to prove it to you, I show you the binary sequences as it's subdivided into the different partitions between the sign bit, the exponent bit, and the fraction bit. So when we do our addition operation, and so for our addition operation, say for instance, we're going to take this representation, which is 1.25, which is on there, right? That's why I want to show everything there. And then 2.5, I want to add 1.25 to 2.5. And so notice the actual value isn't actually there, right? We can't actually encode the resulting operation that's going to add those two together. Because what I should expect is 3.75, right? But when I look at my exhaustive list, I don't have a 3.75. So what I get as a result is going to be a 3.5, which makes sense because that's when I factor in my ability to round after I do my addition is going to be the next assignable value inside of my encoded scheme. Okay, is this really making it more clear what's happening with floating point numbers? It's not how it is lossy on both addition, and it's also lossy on representing actual sets of values. It creates holes in a number line, which has super consequences when you start trying to add numbers together or multiply numbers. Okay. Let's also, let me clear out of this. Okay. So then the next thing I want to talk about then is we already know that we have to go ahead and round with the addition. We'll have to do the same thing with multiplication. But multiplication is kind of an interesting thing because now we can start multiplying by values that are under 1. And so here, we're not going to spend too much time defining the floating point multiplication, but what we will do is we'll take and look at an example with our 5-bit tiny float, just like what we did with addition. They have all these various. Here, let's do, what is this? Yeah, perfect. And let's call this mult. And so here, when we run our multiplication, you can see, here you can see that I have decided to take a value that's under 1 to illustrate one of the interesting novel things in multiplication for floating point values that's not true necessarily for integral values, since you don't have 0.5s, since you don't have values lower, smaller than 1. And then we're going to multiply that by 2.5. And so since this is the same encoding sequence, we can see, yeah, look, we had a 1.25. We know that because I used it in the addition. So we can actually, this is an instance where I did have the number I could represent. And in fact, my number is half the size of my left operand. So just some examples of how we can operate our floating point numbers, but why rounding is a factor and why it's critically so and why you should be aware. Okay, so with that said, I think for the most part, that's the theory that's given to us inside the chapter of the book. So we've really talked about everything that's critical in chapter 2 in terms of how we represent our data in form of binary sequences and how all data inside of our systems at some point has to be quantified, which means represented in the form of a number. And that's true whether it is text-based or whether it is numerical-based. initially, or whether it is an image, or whether it's a sound, or any other format, we as software designers, as software engineers, have to find a way to represent it as a number. And then once we have our number representation, we have our integer types, which we've looked at, and we just looked at our floating point, our fractional types. And so to build off of that, the way that C handles the floating point numbers, so we saw how we're giving a standard generic term of having a sign bit, an exponent bit, and a exponent field and a fraction field. For C, those are defaulted to our float and our doubles. And then, of course, we can try to cast, but we know the casting operations that can happen with those. And so the one thing I want to leave off after talking about our floating point numbers is you can now see if you're building a serious application, and if you have an ability to model it using an integer versus a floating point number, you should always opt to do an integer value. I'll give you an example. If you're going to, up to this point, have you had to implement, we might have already talked about this, but this seems like an apt time to talk about it again, just to highlight this. If you have to create an app that does anything related with managing money, what is the best way to represent money? So it would be ideal. You could see, first of all, you could see the possibilities, the pitfalls, the dangerous idea of representing it using dollar units, right? Because dollar is not the smallest element that defines money. And because of that, dollars naturally, inherently have fractional representations. Like you can have something that is $1 and 0.6, that's 60 cents. Cent is probably, right, if I'm remembering correctly, based off of percent, a percent of a dollar. Okay. But what I've already stated is that money does have a elemental unit, right? What is the elemental unit of money? Yeah, a cent. So now we're going to assume it's a cent for most applications, because you could probably create an argument for some applications where things can then be broken down into partial cents. But we'll make an assumption when we start building the specifications that a cent represents the smallest units of currency. And so if you wanted to make a really solid application, now knowing how fractional numbers work, and that you can potentially have lossy representations when you start adding them or subtracting them or dividing them, and then all of a sudden some money either mysteriously disappeared or appeared because of the rounding behaviors, which could cause all sorts of complexities if that then has to get translated into real money, right? It illustrates why, knowing how that representation is done, you just don't mindlessly say, oh, let me represent this as a float value. Let me represent my dollars in terms of a cent value, and each dollar then will be 100 cents. It might seem like a more clumsy way initially, but one of the values of this class is peering under the hood of our data types gives us a better understanding of when we should use a particular type over another.